When last I left you, I was terrorizing you with equations for some wave functions, right? We had a variety of I guess I had all the n equals 2 wave functions, 2s and the three different 2p orbitals on the screen when we closed out the last video. In this segment, what we're going to do is look at two things. One is we're going to look a little bit at what those wave functions actually mean. What do they tell us? And then we're mainly going to work on writing out electron configurations, looking at how electrons actually occupy those orbitals. Okay, so from last time, we certainly saw that orbitals were mathematically defined, right? They're wave functions, they're just mathematical functions. There's equations that say this is a 2s orbital, right? The way to make physical sense of those is to remember that psi squared is related to an intensity kind of thing. In this case, that means psi squared tells us the probability for finding the electron at a particular point in space. Okay, so if I evaluate psi squared at a particular point, that says that's the chances of the electron being there. I can use that to assess where the electron is more and less likely to be, and that's what we do when we think about what orbitals look like. So when you see a picture of an orbital or an orbital shape, think of those as being made from graphs of psi squared, because that's literally where they come from. So here, for example, we have some pictures on the bottom that describe what s and p orbitals look like, all right? The s orbitals, remember, they come in sets of one, essentially. For each n, I get one single s orbital. I get a 1s, a 2s, and so on, right? Remember, in the equation for that 2s wave function that I showed you, there were no angle terms. There were no theta and phi variables showing up. That means the orbital has to be spherical, right? And so down here on the bottom, we have just the red ball showing us the spherical orbital. The center of that ball would be the nucleus, and that says that's mapping out where is the electron likely to be found. Okay, I will elaborate in a minute. These pictures do sort of overemphasize the idea that this thing is like a sort of a hard-edged ball, because it's really not quite like that. But we'll see that better in some other figures that are coming up. The p orbitals, there's 3 of those for each n value, right? So in 2p, there's 3 orbitals. In 3p, there are 3 orbitals, and so on. They all have this same shape, often referred to as a dumbbell or hourglass kind of shape. In this picture, the white ball in the center, that's the nucleus. And then the red and blue lobes represent the 2 sides of the orbital. The different colors there would, strictly speaking, represent the idea that the wave function is positive on one side and negative on the other, sort of like how the sine wave is oscillating positive and negative. That's what those particular things mean in this case, right? So this orbital is pointed, let's say, in the horizontal direction on our screen, right? It's going kind of like that. If we had the other 2 orbitals in this same n value, they would have the same shape and the same size, but they'd be rotated 90 degrees. So one of them, if this one's going horizontally, one of them would be going vertically. The other one then would be going in and out of the plane of the screen, which is harder to do with my arm and have it show up there, right? But I get this 3 mutually perpendicular orbitals that make up a set of the p orbitals, okay? And that tells us anything that's a p orbital will have that general shape. As the n value goes up, they get bigger, and there's some other complications that get added in, but they all have that same general shape to them. So there's other ways we can look at things from orbitals. This plot here, this is a plot of something known as the radial distribution function. So this is just looking only at the r piece of the function. Okay, you can see on the y-axis here, this is actually 4 pi r squared times psi squared. That's accounts for some of the details of doing the math to get this to scale correctly. But and you can see here the 1s, 2s, and 3s orbitals are all plotted. The 1s orbital is clearly the smallest, right? The maximum in it is in here. That's at that distance that I mentioned before. It's about 53 picometers, the so-called Bohr radius. Okay, my 2s orbital has a maximum out here at a much larger distance, and 3s much larger yet again, right? So we can see all of that. The size of the orbital depends mainly on n. So as I go from n equals 1 to 2 to 3, my orbital gets bigger. There's a little bit of dependence of the size on the L quantum number, and we'll take a small look at that in a moment, okay? Also notice in these plots, this is a good place to get to this idea of the orbitals not having like sharp edges to them. You can see very clearly here that because there are exponential terms in those wave functions, as these things come out to long distances, like say out here, they're coming in and they're decaying exponentially, right? So that means there's no real firm boundary. There's no point at which we can say the electron is never outside of there. Typically, when people draw things like the sphere that was on the previous slide, they do something like figure out the size of a sphere where there's a 95% probability of finding the electron inside of there, say. That's a cut that's typically made, because you just have to cut it off someplace, because the fact that it's an asymptote means you can't totally rule out the idea that it occasionally drifts very far away. This is yet another way of viewing these. So this is still my 1s, 2s, and 3s orbital, in this case viewed as like a cross-section. This figure, I've never really cared for the coloring in this figure, but that shading there represents the electron probability, right? And so it's very clear in this picture how much smaller the 1s orbital is than the 2s, and in turn than the 3s, right? Because if I draw sort of a circle here that contains pretty much everything from the 1s, that's a much smaller circle than if I did the same thing out here for my 3s, right? You can also see in here that there are these nodes, like here and here I've got rings of white space, right? Those correspond in this plot to the fact that I have places where this wave function goes to 0, right? Those are those nodes. And so here they show up as these rings, because that's what would happen if I took this thing and did a cut through the sphere, right? I'd be able to see in there what those look like. So there's lots of different ways that these things can be plotted. These figures are always made by someone just taking the equations for those wave functions like I showed you last time, putting them into Mathematica or some other graphing program, and just playing with the images to get them to look in some way like they want. I have one more of these. This is the set of n equals 3 orbitals. So the 3s is on top, then the 3p, then the 3d. You'll notice that in general, those orbitals look like they're all kind of sort of about the same size, right? They're all on the same scale there, even though there's not any units on the scale. The grid boxes there going on the x-axis are in increments of this Bohr radius, the 53 picometer number that I keep saying. And so if we look at them, they're all about the same size. We know they have different shapes, right? In terms of their energies, the energy of an orbital gets lower, meaning it's more, the electron in it is more tightly bound when the electron can be closer to the nucleus, right? The pull that holds the electron into the atom is the attraction between the positive charge on the nucleus and the negative charge on the electron, okay? So as my electron gets closer and closer to the nucleus, that's gonna lower its energy. It's gonna make it more strongly attached, okay? More strongly attached means it's got a lower energy, means it costs more energy to pull it out of there. The thing that governs the energy sequence for these orbitals, this set, is mainly the fact that the s orbital has this little bump in here, which is not matched in the others. And if I compare the p and the d, the p has this inner local maximum, and there's nothing like that in the case of the d orbital, right? There's nothing there. I know these aren't maybe the easiest figures to see, but that part, we can say that the electron in the 3s orbital can penetrate, can sort of burrow in and get very close to the nucleus on occasion, right? That tends to lower its energy. And so the result of this is that these go up in energy as I go from 3s to 3p to 3d. Okay, so the 3s is at a lower energy than the 3p, and the 3d is at a higher energy still. And that's going to be true for every n shell. As I go up in L, I climb up in energy. As I go up in n, I also climb up in energy, because we saw back here, as n goes up, my orbital gets bigger. That means my electron gets, on average, farther away from the nucleus, and that's going to mean that its energy is increasing, because it's not as tightly bound when it's farther from the nucleus. So armed with those ideas about the sequence of the orbitals, we can almost get ready to start putting electrons in orbitals and doing electron configurations. We have one more thing we have to think about before that, and that is an idea known as electron spin. So electrons turn out to act like little magnets, okay? I drew a little cartoon diagram over here that says I have an electron beam coming in here from the left-hand side, and I shoot my electrons between the poles of a magnet, okay? And if I do that, what will happen is my electron beam will split itself in half, and half of the electrons will be pulled towards one pole of the magnet, half of them will be pulled towards the other pole of the magnet. So my stream of electrons gets split into two different pieces. It does that because the electron has a magnetic moment, and it turns out there are two possible values of that magnetic moment. One of them is going to be attracted towards one pole of the magnet. The other is going to be attracted towards the opposite pole, okay? That electron spin idea is represented by what we refer to as a fourth quantum number. That one is called m sub s, s for spin, okay, it is given values officially referred to as +1/2 and -1/2. The 1/2 part there is because that refers to the magnitude of the electron's magnetic moment in a particular and somewhat quirky set of units, okay? I do want to make a note here that says this is not due to literally to the idea that the electron is a spinning ball, right? We're trying hard to start thinking about electrons as being these delocalized waves. And so the last thing I want to do is think about it explain this by saying, well, if you had a ball with an electric charge on it and it was spinning, that would give it a magnetic moment. That is true. And that is in fact how this spin name got originated, because people were in fact thinking that was what it meant, okay? We don't want to think about that because we don't want to think about the electron as being a particle really at all, or being like a ball, okay? So spin is just kind of a name that got attached to it. In sort of recognition of this fact, the particle physics community now uses some really odd names for other properties that they've discovered. So the people that study quarks, for example, have named some of their properties things like charm and strangeness, because they're trying hard not to get caught out on the idea that like this is called spin and now we say it's not from spinning. All right, so let's talk about how we build up electron configurations, okay? We want to get from knowing about orbitals. Right now what we have is we have an orbital, a set of orbitals, and we can put them in order by energy fairly well based on what we just talked about, okay? Each orbital can accommodate or hold 2 electrons as long as they have opposite spins. That effectively is because if I'm in the same orbital, then I have 3 quantum numbers the same, right? N, L, and M sub L tell me what orbital I'm in. There is a rule that says I can't have 2 electrons in the same atom that have all 4 quantum numbers the same. So I can't have 2 electrons with the same spin be in an orbital together. But if the electrons have the 2 different spins, then I can have them be in the same orbital. We often call those spin up and spin down, and refer to them with arrows or something like I'm sort of doing with my fingers, and you'll see that momentarily. If we want to build up atoms, what we want to do is start filling orbitals with electrons. We want to start at the lowest energy because electrons, if we put them in a higher energy orbital, if there's empty spaces in the lower energy orbitals, they'll just drop down to there, right? So we start at low energy and work towards higher energy. The orbital energy goes up as n increases and it goes up as L increases. So if I do this, what I'm going to try to do is write out the electron configurations for atoms. That's essentially a map that says where are all those electrons in terms of the different orbitals in that atom. So here's a figure that just shows us the energies of the orbitals. It's at least kind of sort of to scale. Okay, I didn't go crazy trying to draw this, but it is reasonably to scale is what I will say. A few things about this. You'll see that in the first column over here, I have all the different s orbitals, 1s, 2s, 3s, 4s. As I go up in n, they go up in energy. As they get higher in n, the steps get smaller in energy, right? So from 1s to 2s is pretty far, 2s to 3s is much less far in here in energy space. In the center column, I have my p orbitals. Notice that here, in each case, I have a set of 3 horizontal lines. Each one of those horizontal lines is 1 orbital, okay? So this set of 2p orbitals there, that's 3 orbitals still. Each one of those 3 different orbitals would be able to hold 2 electrons. When I get to the d electrons over here, now I have 5 of my horizontal lines side by side because I have 5 orbitals in a d subshell, okay? So each one of those horizontal lines represents 1 orbital, okay? Each one of those is a place where I could put 2 electrons. You'll notice most of this is pretty cut and dried. When I get up high here, you'll see that, I'll come back to this idea in a little bit. When I get to 4s versus 3d, for example, these 2 things are at pretty close to the same energy, okay? If I compare starting from 3s up to 4s, I take 1 step in n, so I take a step there. From 3s to 3p to 3d, I've taken 2 small steps up, and I get to very, very close to the same energy, all right? I will tell you that the 4s actually is a teensy bit lower in energy and fills up first. I'll come back to that idea and a way to remember it or keep track of it a little bit later on. So if I'm going to write electron configurations, what I need is a couple of rules. I need something called the Pauli exclusion principle. That says that each electron has to have its own set of quantum numbers. That's the rule that says no 2 electrons in an atom can have all 4 quantum numbers be the same. So the translation of that rule is 2 electrons per orbital as long as they have opposite spins, okay? I have something known as Hund's rule, which for now I'm just going to assert, but I will tell you later how we know it's true. Says the lowest energy state will be one where any unpaired electrons all have the same spin. Unpaired electrons means any places where I just have one electron in an orbital. So if I have multiple orbitals that each have one electron, then I want those orbitals, those electrons to have the same spin. Based on those two rules alone, I can write the electron configuration for any of the so-called representative elements. That's all the elements that are in what I refer to as the S block. That's the 2 columns on the left-hand side of the periodic table, or the P block. That's the 6 columns on the right. Those also are the only elements that we're going to ask you to think about or write electron configurations for in this course. So here's a periodic table to help us. And what I'm going to do is I'm just going to write out electron configurations for the first several elements, okay? So I'm going to give myself some orbitals here. I'm going to write out, say, here's a 1s. I'm not going to try too hard to make this scale in energy or anything like that. 2s, mostly I'm just going to make sure I have room to be able to write in them. Here's my 2p. Let's say I write 3s and 3p in here too. Okay, again, up is increasing energy. All right, I'm going to start with hydrogen. When I get hydrogen, I go in the periodic table. It's atomic number 1. It just gets 1 electron. It goes in the lowest possible energy orbital, which is the 1s. I'm going to represent electrons in my orbitals by arrows. I'm going to write up arrows and down arrows to represent the 2 different spins. I always draw an up arrow first, although there's no rule that says that's a right answer. Okay, so I'm going to do that. If I want to write this out, I could say my electron configuration is 1s1. That says there's the 1s part says what orbital. The superscript part up here, that says 1 electron. Okay. In fact, if you had a collection of hydrogen atoms, half of them would have the plus 1/2 spin and half would have the minus 1/2 spin. They don't all have the same. I just always draw an up arrow first. There's no good reason for that. It's not wrong if you draw a down arrow first. If I wanted to do helium, I would say now I get a second electron. What's the lowest energy place it can go? Answer is it can go in the 1s orbital as well, as long as it has the opposite spin. So helium is just 1s2. Let's skip ahead a little bit. Lithium would look like that, gets 1 more. Beryllium gets 2 more. So if I got to beryllium, I would now have 1s2, 2s2. Right? Because that's just the list of where are the electrons. Get to the 2p's now. So aluminum's easy. That just says I have to put 1 more electron in there, and I'm going to put it here. Again, there's no difference between putting it in that one, putting it in the middle one, putting it in the one on the right. I just always go left to right. Most people go left to right. Okay. The difference between those 3 orbitals there, remember, is which way they're pointed, and the atom doesn't really know which way I called the x-axis or anything like that, right? In actuality, you can't tell those orbitals apart unless you take your atom and put it in an electric field, which actually gives it a sense of direction. That tells it that one direction is different from the others. Now it gets interesting. When I get to carbon, I have choices, okay? Because now I have to put a second electron into my 2p orbitals there, right? I could put it in the same one that I already put one into, or I could put it in one of the others, okay? I'm going to tell you that the way that carbon atoms are arranged is that the electron goes in one of the other orbitals, one of the other 2p orbitals. Then after this, in a moment, I'm going to tell you how I know that and how we can tell, okay? But for now, I'm going to say that the way this wants to be is I'm going to put 1 electron in each orbital in a given subshell first before I double up any of them, okay? So that's my carbon atom. So carbon now looks like 1s2, 2s2, 2p2. Notice there's more information in the arrows than there is in this notation, because over here, if I see the 2p2, I actually have to know some things to know that means it's 1 in each of 2 of the orbitals and not 2 in the same orbital, okay? Nitrogen would look like that. Then if I keep going, I could get to oxygen says, now I have to start putting in the downs because I have to fill in the rest of this set before I go to 3s. So when I get to there, now I'm at argon. Okay, so argon, we could write this as 1s2, 2s2, 2p6. Sometimes people use a notation, which I'll do it for argon, although it doesn't really make any sense for argon. So actually, maybe I'll wait till I get to neon. I'll hop up to neon, I'll do it there. You can see what's going to happen for the other ones, right? If I go over here, I do sodium, I get 1, magnesium, I get 2. I do the same thing again. So this would be aluminum, silicon, that's phosphorus. Then I could do sulfur, chlorine, and this is argon, right? Wait, this is not argon, this is neon, sorry. I said that and I wrote that. 1s2, 2s2, 2p6. So now it's going to make sense to do my little shorthand thing. 3s2, 3p6, please fit on there. Okay. There is a shorthand notation people often use for these, which is we could also write this one by saying it's got everything that neon has, and then I would write the 3s2, 3p6 here. Okay, what that does is if I get further down in the periodic table, suppose I wanted to write out an electron configuration for iodine or something like that, right? It's got, what, 53 electrons, it says there. And so writing out all the superscripts there for 53 electrons would get kind of old, right? It turns out that these electrons that we still write this way, those are what are called the valence electrons, and they're often the most important ones, okay? So that's how we write electron configurations. If you try to write electron configurations for these things in here, these so-called transition metals, some weirdness happens because the way that things fill there is not always as expected. But within my S block, which again is this piece over here or the P's over here, this will always work. You should be able to write any one of those just by looking at where it is in the periodic table. I'm going to talk about paramagnetism for a couple minutes. This is how I know that when I got to carbon, I wanted to put two electrons with the same spin and not a pair in one orbital, okay? Remember that electrons still have this magnetic moment. That's the same cartoon as before of the electron beam splitting in two when it goes through the magnet, right? Magnetic moments, as you might know, depending on your physics background, those are vectors, okay? And so if I have the up arrow spin and the down arrow spin, the reason I'm writing those as arrows really is because they're really vectors, they're angular momentum vectors essentially, right? If I have the up arrow and the down arrow both, they effectively cancel out and then I get no net magnetism, okay? And so if I have two electrons with the same spin and neither one of them is paired, that says that I'm going to have some net magnetism from that, okay? So if I sketch my orbitals back in here real quick, 1s, 2s, I'll just go to 2p this time. And again, the fun started when I got, so at there, here I'm at boron, right? And at boron, I have no choice but to have an unpaired electron, right? So that says a boron atom has a magnetic moment because it's got more up arrows in my picture than down, okay? This magnetism is called, we say it's paramagnetic. Paramagnetism is much weaker than when you think about something being a magnet, like a bar magnet. That's what's called ferromagnetism. That has to do with there being long-range order among domains in a sample of typically iron. That's why it's called ferromagnetism, right? This paramagnetism is much, much weaker than that, okay? But it is measurable, and it is how we can tell, for example, that when I get to carbon, I said, I know that the correct configuration looks like that. The reason for that is I know people can measure that a carbon atom is paramagnetic, and that in fact it has twice the magnetic moment of the boron atom, right? Or of an electron, right? So it has two unpaired electrons. That's a measurable thing, and we can tell. That's how we know those last two electrons have to have the same spin. Likewise, if I went to nitrogen, I can say now it's got three unpaired electrons, okay? And so any time I have a configuration that results in an orbital having just one electron in it, then I have something that's paramagnetic. If all the electrons are in pairs, like if I went back to neon, the word for that is that material is then diamagnetic, which effectively means it's not magnetic at all, okay? So there's just a couple of, sort of terminology details for that. But that paramagnetism, that's how I know, and that's how people made that rule that says you put one electron in each orbital first, right? It isn't just something we made up out of nothing. It is based on observable facts, like the idea that I can see those magnetic moments. So these valence electrons, so this is the next idea. The valence electrons are the ones that I still had written when I did that noble gas notation, right? The electrons in the highest n, with the highest n value, plus any in partially filled d or f shells if I happen to be in the transition metals, which we rarely are in this course, right? But those electrons that are in the highest populated shell, those things are what we call the valence electrons. Okay, those electrons are the farthest away from the nucleus. They have the highest energy. That makes them the most accessible to other atoms. the other atoms. So if two atoms are going to form a bond, we're going to come to say that's because their electrons are interacting, right? And the electrons that can get out and play with the other atom are going to be these valence electrons, right? The ones that are not the valence electrons, like the 1s electrons in a neon atom, those are very, very close to the nucleus because they're so low in energy, right? So they're not going to be really relevant to the chemistry of that atom. The valence electrons dictate the chemical properties of an atom. That's part of why we think about these electron configurations as being important. A little bit about the periodic table and these valence electrons, because this is an important idea, okay? Elements in a column have similar electron configurations. Like if I go down group 1, every one of these elements has a configuration that ends in S1. Every one down here is S2. Come over here and I'm at P1 and P2 and so on, right? And you could write those out and prove to yourself that that's true. Remember also that we said everybody in group 1 makes +1 ions all the time. Everybody in group 2 makes +2 ions. Everyone over here in 17 makes -1 ions, right? So they have similar chemical properties. They tend to do the same thing in their chemical reactions, right? And that extends to other things besides making ions, like carbon forms a compound with hydrogen that's CH4, while silicon forms a compound with hydrogen that's SiH4, and that continues if I go down that column, okay? So the things in a column of the periodic table have similar valence electrons, and they also have similar chemical properties. That's in fact how people first arranged the periodic table, was by sorting things by chemical properties. Now we think of it as saying, well, they're in order by atomic number, and then maybe we talk about explaining it in terms of s orbitals and p orbitals and stuff. But the people who wrote down the first periodic table didn't know anything about that stuff, okay? They just said, these things all act the same. I'm putting them in a group together, and set about doing that, okay? And so now we can correlate that kind of after the fact with how this looks. I have one more periodic table reminder here, and that's about, I promised you I'd give you something about remembering the 4s and 3d issue. The 4s and 3d energy levels are very close in energy, and a lot of you are feeling like it would make more sense if it went 3s, 3p, 3d, and then 4s. Alas, that's not what the atom says it wants to do, okay? The 4s actually fills first for all neutral atoms, okay? How can we remember that? We can remember that by saying we get past 3p. So when I get to argon, when I'm here, I'm on 3p6 as the end of my electron configuration, right? So that's the point where I have to make a decision. Am I going in 3d or am I going in 4s? If I come down, argon's atomic number 18, find atomic number 19, it's over here, it's potassium. Where is potassium? It's in group 1, and that means its electron configuration wants to end in S1, okay? So the periodic table is a good reminder to tell me after 3p, I want to do 4s next, because that's where the periodic table takes me, okay? There's other ways to remember that. People do a thing where you write out the orbitals and draw these diagonal lines through them, but whenever I try and write that out, I always make a mess of it, and so I don't actually use that one. But the periodic table is something, if you're taking a chemistry test, it's almost a cinch that you have a periodic table nearby. In normal times, if you're in chemistry class, it's almost certain there's periodic tables on the wall. And so it's a handy thing and an easy way to make sure you don't make that mistake of going from 3p into 3d next.